Really happy to be back at Flight Software Workshop after a couple years hiatus. It's great to be back here. Today I'm going to speak about NASA's Goddard Space Flight Center SmallSats, a NOS cubed case study. I am Scott Zemerick. Mark Suter was the original author of these slides. I'm just presenting them on his behalf. So if you have any hard questions, hit them up to Mark. He's on the Slack channel. I'll take your easy questions. I want to draw your attention to the bottom of this slide. I'm going to go a little bit into the history of what NOS cubed is, because some of you may not know. It is the NASA operational simulator for SmallSats. I'm going to describe what it is, its architecture, but really this presentation is about how it is evolving and maturing in the past about 3 years. So a little bit about who we are. I also represent the NASA software IV&V program. It's the Katherine Johnson IV&V program. Katherine Johnson was from West Virginia. We are located in Fairmont, West Virginia. I'm colleagues of Cody Cutright, who did the CryptoLib demo earlier today. The goal of IV&V is to provide complete mission assurance to the large NASA missions, all of the Class A missions, and then other missions as well. I represent a subgroup of that, which is the JSTAR ITC team. JSTAR is the John McBride Software Test and Research Team. We also refer to ourselves as ITC, the Independent Test Capability Team. We are experts in software-only simulation, modeling, and emulation. We will model the avionics of spacecraft in order to make and develop a digital twin. We have developed digital twins for Europa Clipper, Psyche, GPM, SLS, James Webb Space Telescope, and several others. We do that, if you want a little bit of background on that, we do that by modeling the behavior at the FPGA level. We model the registers, the DMA controllers, the 1553 buses, the space wire, and we integrate instruction set simulators, such as CIMIX and QEMU. So at the end of the day, we have a complete digital twin, high fidelity simulator for a spacecraft. And that's what the JSTAR team does. What born out of that was in about 2016, we had the question of, could we apply this technique to SmallSats? And we decided to give it a try. So we developed our own SmallSat, STF-1, Simulation to Flight 1. That was the actual physical SmallSat. But as a result of it, the product that came out of that was what we refer to as NOS cubed, the NASA operational simulator for SmallSats. And I'll go into a little bit of its architecture. You can consider this, you consider NOS cubed as a virtual flat sat or a digital twin. And our goal is for it to be a design reference mission for SmallSats. The main development for NOS cubed happened around 2016 to 2019 timeframe. That's when we had a real SmallSat. We developed it for our use. We open sourced it, and it began to gain traction in the community. In 2019, it was the runner-up to NASA's Software of the Year award. And so since 2019 until now, we have matured it and it's evolving. And that's some of the things I want to talk about in a little more detail. We now have more missions. NOS cubed is being supported by more SmallSat missions. And so we are making it more generic. We are rolling in more components. And that's what I want to give you a little bit of feel for. If you look on the right side of the diagram, you're wondering, what is this NOS cube? What is its architecture? In the middle represents the spacecraft, and you have a representative flight software, CFS. You have component simulators that we have developed, such as radio, fine sun sensor, coarse sun sensor, all of your typical components that you would find on a SmallSat. We tie that together with our own middleware, that is a synchronous middleware. On the left side of that, you see Cosmos, or ground station. We've integrated Cosmos. We've also integrated AIT from JPL also. And on the right side of that, you see an integrated dynamic simulator We typically use 42, which is a Goddard product. So when you put all of this together, you end up with a virtual flat sat for a small sat. Out of the box, you get a ready to run flight software, ground and telemetry databases, and simulators of some of the most common components that you would find on a small sat. So it's meant to get you up and running quickly in writing your flight software and defining your command telemetry databases. The goal is to allow you to do development faster, maybe even before your hardware arrives on site. This just shows what the virtual machine looks like. You see visualization from 42. You see the NOS engine part in the middle. That just represents the middleware that's running behind the scenes. On the right, you see Cosmos. On the bottom left, you see your CFS flight software just running. And on the right, in the box that's labeled Sims, this is where we have the running simulators for all of the devices on the small set that you would like to have. Fine sun sensor, coarse sun sensor, radio, magnetometer. So those are out of the box models or sims that we have ready to use. The point of this slide shows that in the last few years, we have been integrated into Goddard's baseline flight software for small sats. And I'm not going to speak to the various missions that you see here. The point is that we have taken these 5 missions. Each have their own reuse, each have their own mission profiles, and we've taken the commonality from them and we're rolling that back into the NOS3 baseline for everyone to use. So we are evolving NOS3 by getting more experience, more small sat missions under our belt, and making NOS3 a more viable and more productive environment for you. And some of the ways we do that is you can think of 5 small sat missions. Yes, they are common in some ways, but they're also very different in other ways. A couple of ways they're different is the different buses. We have low Earth orbit, we have geosynchronous buses. But we support those concepts in NOS3 now. And then the third bullet is what you mainly run when you instantiate a NOS3 virtual machine is a desktop Linux environment. So you can just begin initial flight software development on Linux. And then if you want to build flight software for your other hardware environments and targets, you can also do that as well within the NOS3 environment. So it gives you a little bit of flavor. You start with the Linux on the bottom, and as you can target your hardware as you go. We like to build flight software for various targets, and so we like to have NOS3 build for all these environments. But when we're doing our day-to-day testing and running, we're running on the Linux target. This slide shows our effort to genericize and make the components integrated into NOS3. We have attitude determination control system components such as reaction wheels, GPS, star tracker, magnetometer. On the CNDH side, command and data handling, we have the Space Cube Mini Z and the Mary's Leon 3. For communications, we have an S-band radio model. And for power, we have a generic EPS and battery model. So from the 5 missions that you saw on the previous slide, those 5 missions have specific hardware components from specific vendors. What we have done is we have made those mostly generic so that we could open source these components and make them available to the community. So instead of having vendor X's radio or vendor Y's reaction wheel, we have made a fairly generic interface to these components so that you can use a fairly realistic component as a model as you start to develop your flight software. This slide shows a little bit of how NOS3 can fit into your software and reuse approach. So in the middle, if you take the 5 small sat missions, on the left are the components that have been reused, which means you develop them once. They form the baseline. And you can see in that circle right there, NOS cubed is one of them, along with, generic apps, CFS apps, CFE 6742, and your Cosmos ground system. So those are things that develop one time, they form your baseline. NOS cubed is one of those tools. On the right side, you see your mission specific applications. You see your individual CFS apps for your science. You see device NOS cube simulators, your Cosmos databases, your instrument CFS apps. All of your mission specific software is on the right. So this slide gives you a model of how you can use NOS cubed existing in a generic way, and then roll in your mission specific items as they are defined. I want to talk about the process of how we are developing the generic components. And when I say the word component, you can think of it as just think of it as a generic radio or generic magnetometer or a fine sun sensor. So if you have a component that you're going to fly, you can receive its spec sheet and maybe the actual physical component. You can develop a standalone application, piece of software for it that you can then drop into NOS cubed. And then you can take a parallel path. You can actually use a real flat sat with your component to do your testing, or you can use NOS cubed as a virtual flat sat, roll your software component into NOS cubed, and continue your software development like that. This parallelization of the paths gives you more flexibility. It gets more developers able to write code faster. It puts an environment in front of developers without everyone having to run to the lab, get time on hardware on an actual flat sat, when you can give a virtual flat sat to as many people. You don't have to worry about them getting lab access. You don't have to worry about them breaking anything. They can already learn CFS. They can define maybe their commands and telemetry from the actual component, just using a virtual machine. So this is this is where we have seen the most power of NOS cubed. Going into some of the uses, you can already define your tool chains. You can build for your target hardware, and you can build for your NOS cubed environment. Testing your new applications, you do have to come up with your new commands. You do have to define your telemetry. You have to interact with the hardware at some point. You can use NOS cubed as a precursor to that to do a lot of the groundwork ahead of time. The bullet test integrated apps and flight software. By integrated apps, I mean pretty much a working system. You have to eventually put all of your apps together. You have to have everything integrated, and you have to, run an actual mission profile. I have a slide about this later. It shows you an example. But, NOS cubed is a really good environment for integrating everything into, one place ahead of time, before you have to go and integrate it at a flat sat. The example I'm going to show is on the ADCS algorithm. I have a slide coming up on that. So a few benefits. We've actually captured some metrics, and we've written at least one paper that has some benefits on NOS cubed. The most recent one is it was invaluable during COVID for enabling remote work. It was difficult to get into labs. When everyone went remote, you could easily give NOS cubed to people to continue development and continue testing. So we found that to be absolutely invaluable. Generally, the NOS cubed environment provides a way for people to have a common environment. It reduces the works for me issues. Works for my machine, what's your problem? If everyone has the same environment, this really eliminates that problem. Dry running of procedures, maybe ground scripts. If you can dry run them in a virtual machine, it's much better. Testing, whenever hardware is not available, testing in NOS cubed is the way to go. On our CubeSat, we had one component that took well over a year lead time. I know this is not a problem that's unique to our CubeSat. This is unique to the industry. We were able to develop the software for that component long before we had it. because we had the spec sheet. We generally knew how it behaved. So we wrote a model for it, and then we developed the flight software to go along with it. Operations, you can use NOS3 to perform long duration testing, failure scenarios, and just generally familiarization and training with a SmallSat environment. Out of the box, you can hand this to a new user and they can learn the ground system, they can learn the spacecraft, and they can learn anything in between. If they want to learn about CFS, they can learn about CFS. Maybe they want to know more about the magnetometer that you're using. You can show them the magnetometer model and how it works. So a lot of potential for new people to get up to speed quickly on a virtual environment. This particular slide kind of brings it all together, and this is a recent example of an ADCS from the BurstCube SmallSat mission, and this is what we're trying to gain from NOS3. We want to verify an ACS algorithm closed loop, and in doing this, this one slide shows the integrated part that I mentioned. It shows the ACS algorithm developed by ACS engineers. It shows that being integrated into flight software by flight software engineers. It then shows other engineers actually doing the testing and showing that BurstCube can track the sun and successfully obtain its sun safe mode. And that's what you see here. This is not possible really on Earth with real hardware. We use NOS3 with 42's provided dynamics and inputs, and the goal was to verify that BurstCube would enter safe mode and slew to track the sun after initial tip-off from the launch vehicle. And if you look up there, you can, at the bottom, you see in blue the CSS. The lighter blue, red, and green are the truth from our 42 dynamic sim. The darker values represent BurstCube's tracking. And so at time t equals 0, the coarse sun sensor is starting, and then you see the purple fine sun sensor kick in. And then you can watch the plus y axis that's labeled there, and you can see that it goes and slews a spacecraft up to track the sun. And that's where you see the plus y to the sun at the top. So we were able to verify in NOS3 that BurstCube would be able to slew and enter its sun safe mode and after initial tip-off from the launch vehicle. One cool thing on the right-hand side is that's labeled the 42 sphere viewer. In what you see in the orange or the yellow is the field of view of the fine sun sensor model that we have, and right in the middle is the sun. So that's a really good way to see it track visually. And just so you know, on BurstCube, the plus y axis is the axis that had the solar panels, and that's the reason it was the one we wanted to track the sun. So this kind of shows, this is why we as a team use NOS3 on these missions, is to do closed loop ADCS testing. That's one of our main goals. So NOS3 is open source. And I want to talk, this slide, I want to talk about the path forward for it. So we are and have been rolling in the lessons learned from the Goddard SmallSats into the open source NOS3. We are genericizing components, and you'll see those roll out. That's in progress right now. One lesson that we have learned is we have moved all of our components to a single repository. And what I mean by that is, if you have a fine sun sensor, you may have flight software for it, you may have ground command and telemetry databases for it, you may have a sim for it, a model, and you may have a checkout app for it. Before, we kept all this separate in different repos. We've changed that. That was a little too hard to keep track of. It got a little unwieldy as we had more components and more changes were made. So we now have all components into one repository. So if you need to make a change for a fine sun sensor, it's done in one place. Maybe you need to change a telemetry or a command. It's done in one place now, and it's not done in 3 or 4 different repos that you need to track. So that was a recent lesson learned. We have the goal of maintaining the open source. and making the components be usable, ready to go out of the box for your mission. Eventually, in the summer of this year, question mark, we want this to be a design reference mission. That's always been our goal. We want this to be a SmallSat design architecture and reference mission that you can take, roll the VM, and then start using it on your mission, tailor it as you need, but it gives you a good start out of the box without having to redefine the wheel. We are going to continue to open source the generic components. We would like to incorporate some of the basic ADCS algorithms also inside. That's a goal that we're going to be looking into. We are currently doing a CFS synopsis integration. Jack Lightholder did a presentation yesterday on synopsis, and that will be rolled into NOS3 in the very near future as well. And as always, we are looking to improve the documentation. And I think that's it. So there are the URLs. You can go to NOS3.org. That'll take you directly to this GitHub. And if anyone has any questions, go for it.